Next speaker is Mr. Ron Klemencic from Magnuson Klemencic Associate. Topic to present is Seismic Design Guidelines for Tall Building. Mr. Ron Klemencic is the president of MKA, an award-winning structural and civil engineering firm headquartered in Seattle with offices in Chicago and Riyadh. Let's give him a warm welcome applause.
Well, thank you very much. In my practice in structural engineering, one of the things that's been changing the most rapidly over the last 10 or 15 years has been the seismic design of tall buildings. I can't think of a topic actually that has changed more in terms of how we think about it, how we practice our engineering, and how we apply our skills to these tall buildings in high seismic zones. And it continues to change. And so what I'm going to do today in the brief time that I have is talk about very briefly where we've been, where we are now, and where we're headed in the next couple of years. And as I said, this is a changing landscape month by month, year by year, so it's difficult to keep up with it all, I suppose, at times. So starting with where we've been. Maybe starting in the mid-90s, there was a group of engineers, including myself, that started to ponder another approach to designing high-rise buildings in seismic zones. And anyway, long story short there, for the Council on Tall Buildings entering the picture, a group of folks, including myself, Mike Wilford from Arup, and Andrew Whitaker from SUNY Buffalo, worked on and published this document here, which is entitled The Recommendations for Seismic Design of High-Rise Buildings. This was published by the Council on Tall Buildings in 2008. And if you are interested in this document, which is an excellent overview of state of practice in seismic design of tall buildings, it's available here at the conference out at the CTBUH table. And it does give a good overview of the various topics that are important to think about, but it stops short of giving very specific and detailed recommendations. So I'd encourage you, if you're interested in this topic, to get a copy of this and read it. But this is where we've been. Where we are today, and really the focus of most of my comments is going to be this document, which is something that was written by a similar group of people. But this is the Guidelines for Performance-Based Seismic Design of Tall Buildings. And this document is actually very specific, very precise, and has a lot of very detailed recommendations. This is much more a working guideline for how to do it, whereas this document is more of an overview of the topic. So this is where we've been, this is where we're going, this is where we are, and where we're going is now this document is primarily focused around North American practice. And in our working group session on Sunday, yesterday, it was recognized that this is the case. And what we need to do is extend this to a more global view. And so at the Shanghai conference next year, we're going to be bringing in our colleagues from the Philippines, from Indonesia, from Chile, North America, China, and Japan, to give an overview of seismic design in these various countries and pull together a best practices approach that could be used internationally with the specific aim of making a specific and a conscientious move forward in China. There's so many tall buildings being built in China, it's a high seismic zone, and yet the codes there are still very prescriptive and very restrictive for engineers, yielding buildings that maybe aren't the best that they could be. So that's where we're going. So again, where we've been, where we are, where we're going. So let's move on. I'm going to talk about this TBI guideline for the rest of the time I have. So as I mentioned, back in the 80s and 90s, there were a variety of earthquakes that occurred, in particular in west coast of the United States. It prompted a series of guidelines that were developed primarily for the retrofitting of existing buildings, and you're probably familiar with a lot of these documents. In the mid to late 80s and into the 90s, a new class of buildings started to arise in these cities in San Francisco and Los Angeles, Seattle, et cetera. And the idea there was to start to really challenge the prescriptive language that was in the code, because it was recognized that the building designs that these prescriptive code languages were yielding weren't really user-friendly or architecture-friendly, or in fact, they didn't even perform very well from a seismic point of view. So there was a series of guidelines that were developed in the late 2000s. The City of San Francisco, the Structural Engineers Association of Northern California, the Los Angeles Tall Buildings Council, and here you see the Council on Tall Buildings document in 2008 that was developed. The Tall Buildings Initiative was a funded effort, funded by a variety of organizations, but the idea was that there was this kind of mishmash of activity going on in the world with regard to the design of tall buildings in high seismic zones. And there was a strong desire to pull this together into something that was more thoroughly thought through, so that there was a kind of a beginning and an end and a purpose and a storyline to be told in the design. So this is what the purpose of the TBI guidelines were really endeavoring to do. There are a whole series of tasks that were undertaken here by this group. I won't read all of these, but this was done in partnership with a variety of North American-based organizations. You can see here mostly California-based organizations, but there was strong support across the board to come up with a more comprehensive and detailed guideline. You can see some of the various people that were involved here, a wide range of people, many of the top in their field, from ground motion definition to concrete design, steel design, et cetera. At any rate, the contents of this particular guide here, you see the chapters from kind of introductory comments, but then it gets into very specific definition of ground motions, preliminary design, service level evaluations, maximum considered event evaluations, and the like. Back in the 1990s, there was this, I'd say, fairly well-recognized table that was put together by the Structural Engineers Association in California, and it really kind of summarized the basis of the desire, if you will, what the building code was endeavoring to do. And as many of you know in North America, how the building code still is written is we're basically targeting a life-safe objective under a 500-year event, but because practice up until recently was unable to really go at this demand level very directly due to our constraints of analysis, et cetera, we'd take this demand level of 500 years, divide it by a response modification factor to bring it down to some elastic level that we could actually analyze and design our buildings with. And the hope was that then through detailing, somehow magically, we would satisfy a service level criteria, and we'd also satisfy a collapse prevention criteria. And it was really more of a hope and a prayer. It wasn't really a rigorously demonstrated performance. It was really more anecdotal performance, if you will. So what the TBI guidelines aimed to do was to take a whole new approach. And the new approach was to say, well, what do we really know and what can we define? And what we knew and what we could define was at a service level, and we can argue about how you define a service level demand, but at a service level, we basically want the building to perform well and remain intact. And at a maximum considered event level, and we can argue about the definition of that as well, essentially we don't want the building to fall down. And what happens in between is really difficult, frankly, to assess and predict. And so we focused on defining the demand levels and the acceptance criteria for these two bookends. And that's what this document defines in great detail. One of the things that I'd say is actually fairly poorly done, frankly, in the engineering community, from my experience at least, that is when you go to design a building, to actually write down ahead of time what it is you're going to do in terms of your criteria, your procedure, your approach, and to actually communicate this not only to yourself and to your staff internally, but to communicate that to the external world, whether it's a building official or in many cases in tall buildings, peer review panel. So included in this guideline are specific recommendations on what should be included in such a document. If you're going to communicate in particular to the outside world in the form of a peer review panel, what types of information should you include and how should it be organized and conveyed? Ground motion selection, of course, is really important. The recommendations given in this guideline suggest that when we're looking at tall buildings, that as a minimum we ought to be considering a suite of 7 ground motions, in particular in nonlinear response history analysis, that defining those ground motions should be done either via spectral matching or spectral scaling. I caution everyone that there are hidden bumps in the road with both of these approaches, spectral matching and spectral scaling. If you do spectral matching, the question really is how much real variation in ground motion are you getting and how well are you really testing your building? And in spectral scaling, what you find is if you scale your spectra to the first mode period of your building, you may find great surprises in the second and third mode. The dispersion of the results is very, very important to consider and try to understand what that means to the detailing of your design. And then more recently, there's been a push to use what's called a conditional mean spectra approach, where in fact you use suites of ground motions targeting your first 3 or 4 modes of vibration. This is a really interesting approach academically speaking. The difficulty is there isn't much in the way of, shall we say, historical design information to go by, so it's a bit experimental still at this stage. The guideline then goes into some preliminary design suggestions and in particular points out things that you should think about and be careful with. Our last presenter talked about outriggers. You see here in this particular diagram that remains a question and you need to be particularly careful there. The document also talks about modeling and analysis. It goes into great detail in how you should model the building, what should be included, what stiffness values should be assumed, et cetera. It's in great detail on how the model in fact should be built. When we get into the structural analysis, we're looking primarily at 2 levels, like I mentioned, a service level analysis and a maximum considered level analysis. At the service level, what we're seeking to do is really have little to no damage. The model should comprise all the components of the building, and again, we're modeling this to try and predict the actual response of the building. So unlike the past, where perhaps you were using design material properties and very kind of conservative assumptions in your model, at this stage of the game, we're trying to actually model what we expect the building will really do. And so, for instance, you might, instead of using design values for concrete strength, you're actually in the model putting in the expected material properties, not the design strengths. And these are all detailed in this guide again. There was great debate over what the demand level should be at the service level event. And after actually probably 2 years of pushing and shoving and scratching and biting and complaining and et cetera, it was resolved at this moment in time that the guideline was only seeking to, shall we say, meet the intent of the building code, which is to have a serviceable building under what is, in this case, defined as a 43-year return period event with 2.5% damping considered, noting that high-rise buildings inherently have a lower damping level than low-rise buildings. And then the acceptance criteria at the service level event is essentially elastic behavior. We're looking for the buildings to respond in a very modest way and essentially remain elastic under this demand level. One thing of note, and you probably can't read this, it's far too much data, but what the intent of this slide is to point out is that depending on the city you're in, depending on the seismicity of the city you're in, and depending on the geotechnical conditions of your site, you may find that you have, in this case, let's say in Los Angeles on a Class C site, these various lines represent different return periods. The horizontal line represents the traditional minimum code base shear. And what you see there is, by and large, what we're defining as the demand levels for the service level event and the old code values are very similar to one another. As opposed to if you're in, say, Salt Lake City or Portland, Oregon, where the traditional code minimum base shear is actually substantially higher than the ground motions predicted that are site-specific. And so this might lead you down a path of saying, well, that's great, I can design a more efficient, more economical building. The problem is that, for instance, in Salt Lake City, the maximum considered event is substantial. And so the gap, if you will, between the service level event and the maximum considered event is much greater than it is, say, in Los Angeles. And so if you solely spend your time thinking about the service level event, you will likely get surprised later when you try and demonstrate your building doesn't collapse under substantial ground motions. Load combinations, I'm probably skip over this for the moment. Let's move on to the maximum considered event. So once again, here what we're trying to do is demonstrate that our designs perform in a way that there is a little chance that they collapse or have even partial collapse under this maximum considered event. In most cases, that maximum considered event is considered to be a 2,500-year return period. We're modeling all the components of the building. The analysis is generally done a nonlinear dynamic analysis with this suite of 7 ground motions. And as an acceptance criteria, we've defined 2 classes of elements, or 2 different acceptance criteria, those being for force-controlled elements and those for deformation-controlled elements. Deformation-controlled elements being those that deform and respond in a very ductile way, like beams and bending. Force-controlled elements, say axial load in columns or shear and shear walls, things that when they break, bad things happen. We want to protect against those. We also talk in great detail in this document about soil structure interaction and how this should be treated. You can see on the left that would be the desired model where we include the soil continuum. It's very difficult to do analytically. What's typically done is on the far right. But what we're doing this all is in a 3-dimensional nonlinear response history. And what we've come down with in this report or in the guidelines is that soil structure interaction, while it is permitted, is not required. Now, that said, this document was written for a class of buildings that were probably in the 40, 50, 60 story range. I think we'd all agree if we're talking about buildings that are 800 meters or 1,000 meters, soil structure interaction becomes a far more important thing to think about. So under deformation-controlled elements, and considering those from an acceptance criteria point of view, there is no criteria or imposed limits on those items other than to say that they should stay well short of their maximum fracture demand level. One of the items that is remaining a ponderance and something that we are still scratching our heads over, that is cyclical degradation of elements, in particular how elements such as shear walls degrade in shear and how to model that. And it's a subject that deserves a lot more attention and more research. For force-controlled elements, it's really important to point out here that what we're talking about is we run this series of 7 time histories, and then what we're comparing is 1.5 times the median, or 1.5 times the mean response against the capacity of the elements. So it's a substantial demand on these elements. It's 7 time histories run at the maximum considered event, and then we're taking 1.5 times the median or the mean response level predicted to evaluate whether or not those elements are acceptable or not. We talk about residual drift and transient drift, and I have a whole nother chapter to the discussion here. I'm going to leave that for a future presentation. The point being that with these guidelines then we've actually done a detailed assessment with Sample designs, there were designs prepared by several engineering firms on the West Coast using these guidelines and using several others to benchmark the results. All of that information is available for you if you want to go and get this document off the web. If you go to a website that is peer, P-E-E-R, peer.berkeley.edu, this document is available for free, as well as all the backup reports and the sample designs. So this is an excellent resource. Like I said, it's North American focused, and the kind of next step in this evolving landscape is to engage the rest of our colleagues around the Pacific Rim in particular, and bring that together in Shanghai next year, after which we'll have a more global report and a more international high watermark for seismic design in tall buildings. Thank you.